So, good morning. Introducing the Gauss's law. So we all know that if you have a charge, if it is positive, you have the field lines coming out of the charge, and it was determined that actually you can draw them, you can show their intensity by drawing the arrows or the vectors outwards. And you keep drawing them. If you do this by this size, the next one will be smaller, and they'll keep shortening. And then if you drew them in that form, but as you can see, it will be so laborious for us to draw this kind of field lines. Now the idea is we should just take the number of lines in a given area, such that if we have our positive charge, and then we draw the field lines and just draw continuous lines. So if we can't do this, if we can't draw this kind of diagram to show how the electric field lines keep reducing, then we can draw them continuously, and after drawing them continuously, we now stick to the counting of how many lines are in a given area. So if you took the region around the charge to be a sphere, that is, if I now grab the surrounding of the charge in this form, it means that I'm taking an area of a sphere. So if I get nearer to the charge, like I took this sphere, you can see that concerning the area you are taking of this small sphere, you still have the same number of lines getting out. Do you realize that? Now that means that if you talk of now flux, if you get concerned of about the flux, which is the number of lines per unit area, then the nearer you get to the charge, the bigger the flux. Whereas when you now move away, you find you have a big area. Yes, they are the same number of field lines, but if you get that number of field lines divided by the huge area, now your flux gets down. So the more you move away from the charge, you start getting the flux going down. And we can't do any other, or we can't have any other way of doing that, apart from, borrowing from the ingenuity of Gauss, who came up with the law that the electric flux through the surface S, is given by the integral over this closed surface S, then E dot ds. And this would be the same as 1 of epsilon naught summation I is equal to 1 up to n qi. So if you had a bunch of charges qi, and within a given vicinity, the Gauss's law would be that the dot product of the Benon surface area integrated over this whole region, or by taking the surface of this region, it would be the same as the summation of these individual ones. Of course, where the summation qi is the total free charge enclosed by the surface, enclosed by the surface S. We can make it a little bit nice Since we are talking of the total charge from I is equal to 1 up to n for 2i, so we will get the total. That means that we will have our integral E dot S being the same as the enclosed charge, which is 2n, short for enclosed, divided by epsilon naught. And this is what we call the integral form of Gauss's law. Yeah, integral. There is one repeat after me. So where Q enclosed is the total charge. Enclosed within the surface. The surface S, and this result here is the integral form of Gauss's law. Fortunately, this law helps us as long as we have any surface, we will be able to integrate over that surface, especially if our surface, even if it is a volume, it's only hard to use if you are having a line. Now, the other case would be if you had an application of the Stokes law. Anyone remembers Stokes law? What does Stokes law say? You've forgotten.
Excuse me.
Yes.
So I know you're good at when you do theoretical concepts of physics in real life examples. Is there any example you can really get about the Gauss's law?
What do you mean? I have talked of a charge, and I've showed you how this charge, if it is a positive, you have the field lines coming out of the charge. And then I talk if it is a negative one, the field lines will be going into the charge. Now I have explained how if you want to determine the strength of the electric field around this charge, you need, if you took different places outwardly near the charge, you would be having more lines in same lines, but in a smaller area. Because I drew these vectors becoming smaller and smaller as you get outward from the charge. Now, when you move a step away from the charge, yes, you still have the same field lines, but now the area is bigger. So meaning that shows you that the electric field intensity is now reducing. But the best way to get the idea was now to take the flux, which would be the number of field lines in that area. So I don't know what physical or what real life experience you want me to use when actually we are talking of a charge.
No.
So the differential form of Gauss's law, of course, I was trying to get it in here that if we integral E dot S equal to, I can try it here so that you have the benefit of looking at it in the later. What we got was integral e dot s being the same as q enclosed divided by epsilon naught. We can say that this is the same as the integral of rho the tau over the volume tau, which will give us the total charge divided by epsilon naught. This being the same as integral e dot s. But we know that we can use the divergence theorem, if you remember, and say that this integral of e dot s can be changed into the volume integral by saying that this would be integral of the divergence of e. Then we change now this to the tau, which is the volume. We now integrate over the volume from the surface. So we can transit from the surface to the volume by using the divergence theorem. Stokes' theorem goes where? From where to where? See, that's the problem of semester system. And I know most of you even throw away their notes. Say that course is done. But if you read in the curriculum, you should understand that we say that the prerequisite of electromagnetism is electricity. So you should not throw out those notes if you have to throw them away. If you are sure that you won't meet the same course. Of course, if this is equal to this, so is equal to that, which will be 1 over epsilon naught integral over volume tau, rho d tau. And we know that if we are having two integrals integrated on this over the same variable, then it means that if the two are equal, then the integrands are equal. So this is our integrand. This is our integrand, so it means that if we also take in interest of the constant, then we should be having that the divergence of E is equal to rho over. Now, but we also know that the epsilon naught E is the same as the electric displacement vector D, such that we now can say that the divergence of electric displacement vector D is the same as. So we shall say that the differential form of Gauss's law is that the divergence of D is equal to rho. Of course, where rho is the volume charge density. And D is the electric displacement vector. Not we said that if we got our charge positive, and of course I only draw these field lines in this numerical way, which looks as if it is as if they are coming out of, as if they are in 2 dimensions, because I'm unable to draw the ones which come from here to there, the ones which go here, and the ones which are into the blackboard. But the idea is, if you are going now to take any or apply any of Gauss's law, you must be you must be able to have a symmetrical surface, such that such symmetrical surfaces are, like, for example, a sphere where you can draw a concentric sphere outwards, or alongside this sphere, or inside this sphere, and you call it what we call in electricity and magnetism the Gaussian surface. If it is a volume, so you take, for example, a sphere and take a concentric sphere to be the Gaussian surface. If it is a cylinder, then you have to take another cylinder around the cylinder or inside the cylinder, so you must go what we call a cylindrical surface, which is coaxial. So a spheres share centers, so we call them concentric. And then when we talk of cylinders share an axis. So we call them coaxial. If we draw one, women share a man, so we call them co-wives. But forget about that. Whereas if we have a surface which is linear, then we draw what we call a pillbox, a Gaussian pillbox. So you remember when we were taking the dielectrics, we drew a pillbox spinning on the top of the dielectric and to the bottom of the dielectric, and they were only sharing an interface. And then we said that we were taking a Gaussian pillbox. So the thought is that in order to apply Gauss's law, then we have to make sure that we are dealing with surfaces which are spherical. So symmetry is very crucial. It's very crucial in the applications of, just let's say, in application of Gauss's law. That's why we talk of a concentric around the sphere. We draw another sphere, or is either outside or inside, because there is symmetry. If you are on this side of the sphere, there is another. If there is one field line coming out of this side, there is another one coming out of this side. That's what we call symmetry. If this field line is going this way, there is another one on the other side. If you have radial field lines coming out because of the line charge in the center of the cylinder, you still got the field lines coming this side, going inside. One going up, going down. Questions? Case of spherical symmetry. We choose, for convenience, we choose the Gaussian surface. We choose the Gaussian surface, a sphere, concentric with the charge distribution. Charge distribution, and we shall start by doing an example so that we get this point clear. That is to find the electric field intensity find the electric field intensity at points outside and inside uniform spherical charge distribution. Spherical charge distribution of charge having a charge density rho naught and radius capital R. Okay, so now we are looking at a bunch of charges, and after having this bunch of charges, we want to know either outside the charge distribution. So I normally use an example of entungo. How many of you know entungo? These women are crafty that they they are so artistic. I'm not sure they're fan of eating them. I wonder who makes them. How do they make them? With their hands and then I'm a bit selective.
But they ban them.
No. I'm a bit choosy in a way. Pardon? Yeah, selective. I mind what I put in my good stomach. Okay, but those women make them, and they make crumbles of seeds of simsim, I think with sugar. And then I normally used to see guys squashing them. Yes, so let's take each of the pieces or each of the seeds of simsim to be a charge. And this charge giving out an electric field. So first, for the outside, we shall try now to draw a concentric sphere around that entungo, okay? And then, but before then, it means that this is our entungo, so this is one outside. So we have our entungo. And I won't really draw much. I'll just maybe shade it, but I can't use the dots. I don't have really that time to make the dots. So this is the center, and this is our radius. So because of the some defect of each of the seeds of the entungo, you have now this field lines coming out. I'm not going to draw the field lines. So we have the field lines coming out of radial, along the radius all over. And we are drawing a fictitious, mathematically fictitious, what? Surface for convenience to be able to do our calculation. And we shall give this surface our name of being a Gaussian. And then we have R, small r being the radius of the Gaussian surface. Now, we have two sides of our Gaussian law, our Gauss's law. And this Gauss's law is that the integral over this closed distribution of our entungo, E ws, is equal to the total enclosed charge divided by, so we got this as 1 over epsilon naught, integral over the volume tau, rho d tau. So there we are. So it means that the total charge, so first on the left, it means that we are taking the closed surface. Fortunately, we are now enclosing the whole Tungo. So the whole Tungo is enclosed. So on the left-hand side, we shall be taking the ds is the volume of, is the surface area of the whole Tungo inclusive. But we shall be talking of the small r. Whereas the exercise I will give you, since time is not my best friend, will be for you, you'll have to take the inside. If time doesn't allow you to finish this. So with this now, I apply, because of the spherical symmetry, E, the electric field intensity, is constant. It is constant at all points. On S. What we are saying, if you move around the surface of our sphere, at each point, the electric field intensity will be the same because it moved from the center to because the radius of that surface is the same. And you know that E is equal to Q over 4 pi r squared, where r is this distance. So E is the same at each point on the surface of our Gaussian surface. And is on all points on S and is directed radially outward. Outwards. So it's along the radius and it's coming from the inside and getting out. So if we invoke Gauss's law, or by invoking Gauss's law, we can substitute in the values we know and then get out the expression for our electric field intensity. So by Gauss's law, we have that the integral over the closed surface EDS is the same as 1 over epsilon naught integral over the volume tau, rho naught, the tau, remember rho naught is the volume changes that they gave us in the question. And this would imply that by putting E outside, we can integrate our surface, so we shall get the total surface area. I'm just removing, I'm forgetting about the vectors for the sake of finishing now. After all, we know that vectors are passing in one direction, okay? So I will have the E into the surface area of the Gaussian surface. So that means the surface area of the sphere is 4 pi, and this will be the same as 1 over epsilon naught integral. So we take rho naught over epsilon naught, and then we are integrating the whole volume. So we are taking the volume of the whole Tungo. Only the Tungo, because it is the Tungo which is contributing the total enclosed charge. And that's why when we came here, we say that it is the volume of the sphere made of the Tungo. Because yes, you are having the surface as big as small r, but the only thing that is contributing to the charge and giving you the electric field that you are talking about is only the charges which are in your distribution, which are received in your Tungo. So I can only go as far as the volume, the radius of the Tungo, and that's why I get 4/3 pi capital R cubed. Pardon? And that's why we have now This way having a capital R, and this here we have a small r. The total enclosed charge is that enclosed charge within the tumor, which will be the volume of the of this tumor times the charge density of the tumor. Okay? So rho naught times this is when you get the Q and rho. So I do the chopping of the pi's, the r's, and the like, and then I will come up with E is equal to, so you can put here your vector if you want, and put the R cap on the other side. You haven't changed anything, okay? The other one is the unit direction vector, and where R cap is the radius, I mean the unit direction vector along the radius. So our E would be the same as rho naught over 3 epsilon naught R cubed divided by R squared R cap. And this is for when we take the Gaussian surface being greater than its radius being greater than the radius of the tumor, or by encrypting our, or I mean by describing our Gaussian surface outside the charge distribution. Now, I will only step the other one and do the business. I'm now going to chop off, going to be so artisan, and chop off some seedlings of the tumor of our tumor. Okay? Or some guy is going to cheat me. Imagine if these women was one of your aunties or your mom. And I say your mom, some of you say no, mom is the mom. So I'm going to only reach up to this point, and that is that you always go in this basket and chop off systematically, chop off the seeds around that, but leave it still, I mean, spherical. So like you chop off some layer, all of them, and make them uniform. So that's how you cheat before you got served. So I'm going to chop off a few of them, and now my Gaussian surface is inside. So if my Gaussian surface is inside and I've chopped off some stuff, I'll still apply the Gauss's law. And when I apply Gauss's law instead, the only change that I will get, this now is inside. So B, this is inside. So for points inside the spherical distribution, now these guys been told that they can be in the library when the lecture is going on. They are fasting. That's why I asked. Have they been told? And what did you do?
This one is from the side here, QE.
From area of economics. So, okay. So for these points, we shall apply also Gauss's law. So by invoking Gauss's law, so we know that integral E dot S is equal to 1 of epsilon naught integral rho naught tau over the volume tau over the surface S. Now on the left side, this is enclosed surface. So the only enclosed surface is that we have to have it in our mind that where we put dotted lines is what was left after this kid, chopped off a bunch of some of the seeds out. So that's our Gaussian surface. So we have our E, E nu 4 pi r squared small. Okay? But this would equal to rho naught of epsilon naught integral the total volume left, and what is left is small r, because the capital R now was reduced. This kid chopped off a bit of our seed, so we can only say for that pi small r cubed as our volume. And then we get our simplification resulting into E is equal to, I'm jumping a couple of steps, being rho naught over 3 epsilon naught, then R cap. This is for R less than capital R. When you take the Gaussian surface to be inside, then tungo. Yeah, there is an R up here which remains when you chop the R. So in summary, we can write it in a nice way that E is equal to either rho naught over 3 epsilon naught R cubed over R squared R cap when you have R greater than capital R, or could be rho naught over 3 epsilon naught R, then R cap for when R is less than. And we can graph this, that on graphing the above, then we got that our electric field intensity would be linear. If you look at this, when you are inside, it will be proportional, because this is a constant. E would be proportional to R until when you reach the surface of the tungo. Okay? So if you kept drawing the Gaussian surfaces, it would be proportional until when you reach the surface of the tungo. And then when you reach the surface of the tungo onwards, it will start now varying inversely proportional to the square. And this is the radius of the Gaussian surface, R. And this is E. This is proportional to 1 over R squared. And this is proportional to R. So now we know how the electric field intensity behaves by just looking at the case, the spherical case. Tomorrow we shall look at the cylindrical case. And then Thursday we should be able to do a couple of more other examples and probably be able to move on to better things in the course. Any query? Okay, see you tomorrow. Find it there.